Right. Let's begin with linear motion. Now, motion is the progressive or continuous change of position by a body. Linear motion is the motion of a body in a straight line. It is also called translational or rectilinear motion. Other types of motion are circular and oscillatory. Circular motion occurs when a body moves along a curved path. It is also called rotational or curvilinear motion. Oscillatory motion occurs when the movement repeats itself about an equilibrium position due to a restoring force, for example in a pendulum or a spring. It is also called periodic or vibrational motion. In this chapter, we shall only deal with linear motion. Let's start with distance and displacement. Now, distance is the length of the path covered by a moving body. Consider a car moving from point A to B along a curved road. If the length of the path is 650 meters, then that is the distance covered by the car. When describing distance, we ignore direction. We just state the magnitude or the size of the distance, and so distance is a scalar quantity. On the other hand, displacement is the change in position of a body. It is the distance moved in a particular direction, denoted by S. For displacement, both magnitude and direction are considered, and so displacement is a vector quantity. When describing displacement, we are only concerned about the initial and the final position. The path followed is not important. So in the case of our car, displacement is the length of the straight line from A to B. So we say displacement S is equal to 350 meters due north. So if a person drives from his home to work a distance of 15 kilometers and then back home, he has covered a distance of 30 kilometers. The displacement, however, will be zero. Displacement from home to work is positive, and from work to home is negative. Next, we look at speed. Speed is the distance covered per unit time. Mathematically, speed is equal to distance covered over time taken. The units are meters per second or kilometers per hour. This definition, however, only applies for an object moving uniformly over a period of time, but in most cases, this does not happen. For example, consider the man driving from his home to work a distance of 15 kilometers and takes 1 hour. If we calculate speed, we get 15 kilometers per hour. Does that mean that the speedometer of the car was constantly indicating 15 kilometers per hour? Not at all. The speedometer was constantly fluctuating. In fact, at some points, like a traffic light, it would indicate 0, and maybe 5 kilometers per hour during traffic snarl-ups, and 60 kilometers per hour on the freeway. So we talk about average speed, and we say average speed is equal to the total distance covered over the total time taken. And that total time includes the time that the car was at rest. The units of speed, meters per second and kilometers per hour, are interconvertible. We know that 1 kilometer is equal to 1,000 meters, and 1 hour is equal to 3,600 seconds. So to convert meters per second into kilometers per hour, we multiply by 3,600 over 1,000. And to convert kilometers per hour into meters per second, we multiply by the reciprocal, 1,000 over 3,600. And so 50 meters per second will be equal to 50 times 3,600 over 1,000, which gives us 180 kilometers per hour. 90 kilometers per hour will be equal to 90 times 1,000 over 3,600, which gives us 25 meters per second. Next, we move to velocity. Now, velocity is defined as change of displacement per unit time. It can also be taken as speed in a specified direction. Mathematically, velocity is equal to change of displacement s over time t. The SI unit of displacement is meters per second. If the displacement is the same at equal time intervals, the body is said to have uniform or constant velocity. But it is unlikely that a car maintains uniform velocity over a long period of time, so we talk about average velocity. Average velocity is equal to total displacement over total time taken. Now, is speed and velocity synonymous? Yes, in common language they are synonymous, but in science they are not. Speed is a scalar quantity, while velocity is a vector quantity. Speed has only magnitude, whereas velocity has both magnitude and direction. Speed depends on the magnitude of the path length described by a body and the time taken to describe this path. Velocity, on the other hand, depends on the displacement of a body and the time taken. Now, when a body moves in a straight line throughout its motion, the magnitude of displacement is equal to distance. In such a case, the magnitude of the average velocity is equal to average speed. Let's take an example. A car moves 60 meters due east in 6 seconds and then 80 meters due south in 8 seconds. Calculate its average speed and average velocity. Average speed is equal to total distance over total time taken. That is equal to 60 plus 80 meters over 6 plus 8 seconds, and that gives us 140 meters over 14 seconds, which is equal to 10 meters per second. Average velocity is equal to total displacement over total time taken. We first calculate displacement. If we plot the motion 60 meters due east and then 80 meters due south, we have a right triangle. Displacement is the hypotenuse. Using Pythagoras theorem, s squared is equal to 60 squared plus 80 squared. That is 3,600 plus 6,400, which gives us 10,000. And so s is equal to 100 meters. So average velocity is equal to 100 meters over 14 seconds, which gives us 7.14 meters per second. Are we done? Not yet. We still need direction. We put a compass at the initial position. Then we find the angle theta. Tan theta is equal to 80 over 60. And that gives us tan theta is equal to 1.33. And if we find the inverse, we get theta is equal to 53 degrees. So from north, this is 90 degrees and then another 53 degrees. And that gives us 143 degrees. So average velocity is 7.14 meters per second on a bearing of 143 degrees. Let's move to acceleration. Acceleration is the change of velocity with time. Mathematically, acceleration is equal to change in velocity over time taken. When the speed of a moving object increases with time, we say the object is accelerating. The velocity changes from an initial velocity u to a final velocity v during a time t. And therefore acceleration is equal to v minus u over t. The SI units of acceleration is meters per second squared. Acceleration is a vector quantity and changes with the change in the magnitude of velocity, direction of the velocity, or both. When a body's velocity reduces with time, for instance, when brakes are applied to a moving car, the final velocity v will be less than the initial velocity u. So v minus u over t will be a negative. This negative acceleration is called deceleration or retardation. For example, a car is moving at a constant velocity of 180 kilometers per hour. Brakes are applied and the speed reduces to 72 kilometers per hour in 10 seconds. Calculate the acceleration of the car. So acceleration is equal to v minus u over t. We first convert the velocities into meters per second. Initial velocity u, 180 kilometers per hour, will be equal to 180 times 1,000 over 3,600, giving us 50 meters per second. And final velocity v, 72 kilometers per hour, will be equal to 72 times 1,000 over 3,600, giving us 20 meters per second. Acceleration will be equal to 20 minus 50 over 10. That gives us minus 30 over 10, which is equal to minus 3 meters per second squared. Right, let's now move to motion time graphs. Now the variation of distance, displacement, speed and velocity over a given period of time can be plotted in a graph. Let's look at the common motion graphs. We start with distance time graphs. These graphs show how distance varies with time. We start with the distance time graph for a stationary body. Now a stationary body is also said to be at rest. It is not moving. But remember, time is always moving. So at time t is equal to 0 seconds, the distance covered is 0. After 10 seconds, the car hasn't moved, and so the distance is still 0. At 20 seconds, the distance is still 0. And at 30 seconds, it is still 0. So the graph of distance against time for a stationary body is a straight line along the x-axis or the time axis. Second case, a body moving with uniform speed. Now the distance covered by a body moving at uniform or constant speed changes uniformly at equal time intervals. For example, at time t is equal to 0 seconds, the distance covered is 0 meters. The car starts moving, and after 10 seconds, it has covered 20 meters. After another 10 seconds, it covers yet another 20 meters. And in the next 10 seconds, it covers another 20 meters. So the distance time graph for a body moving with uniform speed is an inclined straight line through the origin. As you can see, the distance covered is equal for equal intervals of time. In this case, for every 10 seconds, the car moves 20 meters. The gradient or slope of a distance time graph gives the speed of the motion. In our case, the speed will be 2 meters per second. So we can have a graph of a body that starts from rest, covers a distance of 20 meters in 10 seconds, remains stationary for 15 seconds, and then covers another 30 meters in 10 seconds. Third case, a body moving with variable speed. It means the speed is either increasing or decreasing over time. When the speed increases, it means the body covers a given distance over a shorter period of time. For example, let us use our car. At time 0 seconds, the distance covered is 0 meters. Then for the first 10 meters, it takes 15 seconds. But the next 10 meters, it takes 10 seconds. And the next 10 meters, it takes 5 seconds. And in the final 5 seconds, it covers 20 meters, which is 2.5 seconds for every 10 meters. So the graph will be a curve like this one. What if the speed is decreasing? A decreasing speed means the car takes longer and longer to cover a given distance over time. For example, let's take a car moving with uniform speed and takes 10 seconds to cover 30 meters. Then it takes another 5 seconds to cover 10 meters. And then a whole 10 seconds to cover yet another 10 meters. And finally 15 seconds to cover the same distance of 10 meters. So the time taken to cover 10 meters is increasing from 5 to 10 to 15 seconds. The graph is therefore a curve like this one. Next, we move to speed time graphs. These graphs show how speed changes over time. We use a speedometer to study these. First case, speed time graph for a stationary body. For a body at rest, it means the speed is 0 meters per second at time t is equal to 0 seconds. At time t is equal to 10 seconds, the speed is still 0 meters per second. At time t is equal to 20 seconds, the speed is still 0 meters per second. So the graph is a horizontal line along the time axis. Second case, a body moving with uniform speed. It means the speed does not change with time, but remains fixed or constant at a given value, which is not 0. So if a car is moving at a uniform speed of 40 meters per second, then at time 0 seconds, the speed is 40 meters per second. At 10 seconds, it is still 40 meters per second. At 20 seconds, it is still 40 meters per second. So the graph will be a horizontal line at the 40 meters per second mark. And the third case, a body moving with speed varying uniformly. This means the speed increases or decreases as time goes by. For example, a car starting from rest and speeding away. At time t is equal to 0 seconds, the speed is 0 meters per second. After 10 seconds, the speed is 20 meters per second. After another 10 seconds, the speed is 40 meters per second. And after another 10 seconds, the speed is 60 meters per second. So the graph is an inclined straight line through the origin. Now if the speed remains constant at 60 meters per second for 10 seconds, then the graph flattens at this point. Now suppose the driver applies brakes and brings the car to a stop in 20 seconds. It means the speed will reduce from 60 meters per second to 0 meters per second in 20 seconds. So we have this graph. Third type of graphs is displacement time graphs. The first case, the displacement time graph for a stationary body. Now just like distance, the displacement of a body does not change with time. But displacement is a vector quantity, and the position of the body may be negative or positive relative to an observer or a reference point. So the displacement axis is negative and positive scales. If we take the front of the observer to be positive, a body stationary 20 meters in front of the observer will be represented by a horizontal line at the 20 meters mark. And a body 30 meters behind the observer will be represented by a horizontal line at the negative 30 meters mark. Second case, a body moving with uniform velocity. Like in the distance time graph, the displacement of a body moving with uniform velocity changes uniformly at equal intervals of time. That means the body covers the same distance in equal time intervals in the same direction. For example, here, the car covers 10 meters every 5 seconds moving towards the right. The gradient or slope of a displacement time graph gives the velocity of the motion. Third case, a body moving with variable velocity. Just like in the distance time graph, the body starts from rest and travels through a distance s meters in time t seconds. The displacement varies over equal time intervals. The graph is a smooth curve. This curve represents a situation in which the velocity increases with time. In other words, the body is accelerating. From this graph, we can calculate two components of velocity: average velocity and instantaneous velocity. We start with average velocity. Let us pick 2 points A and B and look at the motion between these 2 points. S1 and S2 are the positions of the car at time t1 and t2 respectively. Delta S is the displacement from A to B given as S2 minus S1. And delta T is the time interval between A and B given as T2 minus T1. The average velocity is the ratio of the change in position delta S to the time interval delta T in which the displacement occurs. In this case, delta S is equal to 42 minus 10 giving us 32 meters, and delta T is equal to 7 minus 3 giving us 4 seconds. So average velocity is equal to 32 meters over 4 seconds, giving us 8 meters per second. Next is instantaneous velocity. Now we talked about the speedometer of a car fluctuating constantly during motion. The speedometer reading gives the velocity at that instant, called instantaneous velocity. It represents the rate of change of displacement at that instant of time. To get the instantaneous velocity, we mark a point on the graph at which the instantaneous velocity of the body is to be calculated. Then we draw a tangent to the curve at that point. The slope of this tangent represents the instantaneous velocity at that point P. Slope or gradient is given as delta S over delta T, or as tan theta. And so the displacement time graph allows us to find the total displacement and velocities of a moving body. But while the graph can also indicate acceleration, we cannot use it to calculate this acceleration. We can only calculate velocity using such graphs. So if a car starts from rest, gains speed and moves with uniform velocity for some time, then brakes are applied and its velocity gradually decreases and the car finally comes to a stop, the motion graph is as shown here. This point here is the car at rest, and we can see the displacement is 300 meters. Time taken is 22 seconds, and so the average velocity will be 300 meters over 22 seconds, and that gives us 13.64 meters per second. Now, considering that displacement takes into account the direction of motion, suppose a car starts from rest and covers 40 meters in 20 seconds, and then reverses back to the 10 meters position in 10 seconds. The displacement time graph would look like this. In this case, if the forward direction is taken to be positive and the backward direction taken as negative, the displacement will be 40 plus minus 30, giving us 10 meters. But the distance time graph would look like this. In distance, direction does not matter, and here the distance covered will be 40 plus 30, giving us 70 meters. fourth type of graphs is the velocity time graphs. These graphs tell us how velocity changes with time. They look exactly like the speed time graphs. And that is because for a body moving in a straight line, the magnitude of its speed is equal to its velocity. So speed and velocity are one and the same thing. First case, for a body at rest. Now for a stationary body, the velocity at all times is equal to 0. So the graph is a horizontal straight line along the x-axis. Second case, a body moving with its velocity changing uniformly. This means that the velocity increases or decreases by equal magnitude over equal intervals of time. We say the body has uniform acceleration. The graph is an inclined straight line through the origin. If you take any 2 points P and Q after times T1 and T2, V1 and V2 are the corresponding velocities. Gradient of the line is equal to delta V over delta T, which is equal to V2 minus V1 over T2 minus T1. This gradient is equal to the acceleration. And since the graph is a straight line, its gradient is a constant and hence constant or uniform acceleration. Third scenario, a body moving with its velocity changing non-uniformly. This means that for equal intervals of time, the velocity increase or decrease is non-uniform. Like in the speed time graph, we have an upward curving graph for accelerating velocity. From this graph, we can calculate average acceleration and instantaneous acceleration. Let's start with average acceleration. We take any 2 points, say A and B, on the curve and consider the motion between them. V1 and V2 are the velocities of the car at times T1 and T2 respectively. Delta V is the velocity change from A to B, and delta T is the time interval between A and B. The average acceleration is the ratio of the change in velocity delta V and the time interval delta T, and this is equal to V2 minus V1 over T2 minus T1. Next is instantaneous acceleration. This is the acceleration at an instant. It is equal to the tangent to the graph at that point. Because this graph represents increasing acceleration, gradient at point Q is greater than gradient at point P. For a decreasing acceleration, the graph curves the other way. For this one, gradient at S is greater than gradient at R. Note that decreasing acceleration does not mean deceleration. Deceleration is negative acceleration. When a car brakes and its velocity reduces uniformly, the graph is an inclined line with a negative gradient. This gradient represents deceleration or retardation or negative acceleration. So for a body starting from rest, its velocity increases up to a certain level. It travels at this velocity for some time before brakes are applied, and the velocity reduces to 0 when the car comes to rest after some time. This is the velocity time graph for that motion. Right, let's talk about the area under a velocity time graph. Now consider a body starting from rest and moving with a constant acceleration for time t seconds. The velocity time graph will look like this. If the velocity of the body after t seconds is equal to v meters per second, then the distance traveled will be equal to the average velocity times time. Average velocity is given as the initial velocity plus the final velocity over 2. Since the body started from rest, the initial velocity will be 0. So 0 plus v over 2 gives us v over 2. Then we multiply by t. That gives us half v times t. If you look at this expression, it is the same as the area of a right-angled triangle with a base t and a height v. So the area under a velocity time graph is the distance covered by the body in t seconds. Let's look at another one for velocity time graph. Again, velocity is a vector quantity, and so we have positive and negative velocities. Positive means moving forward, and negative means moving backward. Not moving is where we are crossing the x-axis, and here it happens twice. So what's happening at these points? These flat sections mean uniform velocity. The velocity is not changing with time. So here, the object moves at 6 meters per second for 1 second. And here, it moves at -3 meters per second for 3 seconds. Uniform velocity also means zero acceleration. This part with a positive gradient means positive acceleration. Velocity is changing with time. This section is also positive acceleration, but the acceleration here is larger because the gradient is greater here. This section with negative gradient is negative acceleration or deceleration. Now, important to note from this graph is that if you are moving away from the reference point, then you are accelerating or speeding up. Whenever you are moving closer to the axis, you are decelerating or slowing down. So what about this section? Well, you are moving away from the reference point, and this means you are speeding up, just in the opposite direction. Let's move to something else, measuring speed, velocity and acceleration using a ticker tape timer. A ticker tape timer is used to measure the velocity and acceleration of a body. It uses an alternating current to make a flexible metal strip move up and down at a frequency of 50 Hz or 50 times per second. Each time it moves down, it presses on a piece of paper and leaves a dot on the paper. It therefore means that the ticker timer makes 50 dots each second. So if the paper is moving, the dots are spread along the paper. We can therefore work out the velocity by measuring how far the tape has been pulled through, and we can find the time from counting the dots on the tape. Because the frequency is 50 Hz, it means the time between two dots is 1/50, which is equal to 0.02 seconds. Let's see how we analyze the dots on a ticker tape. Now, the motion of the object pulling the ticker tape can be determined from the distribution of the dots on the tape. The closer the dots, the slower the motion. The farther the dots, the faster the motion. The first strip shows the slowest motion of the 3 strips. The second one is faster, and in the third strip, the dots are farthest apart, indicating the fastest motion. Let us analyze another set of 3 strips. In the first one, the dots are uniformly distributed. This indicates the object is moving at uniform velocity. In the second strip, initially the dots are close to each other. The distance between the dots then increases uniformly. We know that when the distance between the dots increases, the velocity of the object increases. It means the object was accelerating. And in the third strip, the distance between the dots decreases over time. This indicates the velocity decreases with time or retardation. and therefore, the motion of an object can be determined by studying how the dots are distributed. Ticker tape charts can be constructed by cutting the ticker tape into short lengths with equal number of dots on each length and sticking the strips side by side in the same order that they were on the whole tape. Let's look at calculating velocity using a ticker tape timer. We know that the velocity of a motion can be found by the formula V is equal to S over T. In a ticker tape, displacement can be measured directly from the length of the tape, and the time taken is determined by counting the number of ticks between the length measured. We, however, need to know that T is the time taken from the first dot to the last dot of the distance measured. The time between two dots is called a tick, so we count the number of ticks between two dots. Each tick is 0.02 seconds for a frequency of 50 Hz. For example, this figure shows a strip of a ticker tape that was pulled through a ticker tape timer that vibrated at 50 times per second. Let us find the average velocity of the motion. The distance from the first dot to the last dot is 15 centimeters, which means the displacement is 15 centimeters. To determine the time, we count the number of ticks, that is the spaces between the dots. There are 15 ticks. Each tick is 0.02 seconds. So total time is 15 times 0.02, which is equal to 0.3 seconds. Velocity is equal to displacement over time, that is 15 centimeters over 0.3, giving us 50 centimeters per second. Next, finding acceleration from a ticker tape timer. Now, we know that acceleration is determined by the formula A is equal to V minus U over T, where A is the acceleration, V is the final velocity, U is the initial velocity, and T is the time taken for the velocity change. Now, this is important. T in this case will be the time taken from the initial velocity to the final velocity, and not from the first dot to the last dot as we did when calculating average velocity. From this tape, the initial velocity U can be determined by measuring the length of the first tick and then divide by the time taken. The final velocity can be determined in the same way. Usually students would have no problem with these steps. The problem arises when finding the time taken. There are 5 ticks from the first dot to the last dot. However, these 5 ticks is not the time we want. As we mentioned, time taken is the time between the initial velocity U and the final velocity V. The question is, where are U and V? Since U and V are average velocities, they are in the middle of the ticks. For example, U is in the middle of the first tick and V in the middle of the last tick. So the time between U and V is 4 ticks. This step is very important in finding acceleration and is the major source of errors among students. Let's take an example. This ticker tape was produced by a toy car moving up a tilted runway. If the frequency of the ticker is 50 Hz, calculate the acceleration of the toy. We first determine the initial velocity U, final velocity V, as well as the time taken from U to V. In the first tick, time is 0.02 seconds because we are talking about 50 Hz, and the displacement is 5 centimeters. So U is equal to 5 centimeters over 0.02 seconds, and that gives us 250 centimeters per second. In the last dot, time is also 0.02 seconds. but displacement is 1 centimeter, and so V is equal to 1 centimeter over 0.02 seconds, giving us 50 centimeters per second. Now the time between U and V. U and V are in the middle of these positions, so the time between U and V is 4 ticks. If each tick is 0.02 seconds, then this will be equal to 4 times 0.02, giving us 0.08 seconds. And acceleration is equal to 50 minus 250 over 0.08, and that gives us minus 2,500 centimeters per second squared. Negative acceleration is also called deceleration, and that is expected because the toy car was moving up the runway. Let's take another example. This figure shows a strip of a ticker tape for the motion of a trolley moving down an inclined plane. If the frequency of the ticker tape is 50 Hz, what is the acceleration of the trolley? We find U, V, and T. The direction is towards the right, so this is the first dot. Here, we are given that the trolley made 5 ticks to move 5 centimeters. The displacement is 5 centimeters, and the time is 5 ticks, which is equal to 5 times 0.02, which is equal to 0.1 seconds. So U will be 5 centimeters over 0.1 seconds, giving us 50 centimeters per second. At the other end of the motion, the trolley took 5 ticks to move 10 centimeters. So displacement is 10 centimeters, and time is 5 times 0.02, which is 0.1 seconds. And that means V is equal to 10 centimeters over 0.1, giving us 100 centimeters per second. Now it's time to find the time interval between U and V. Where is U and V? Is it between the first 2 dots and the last 2 dots? No. Because we used 5 ticks for calculating U and V, then U and V must be in the middle of the 5 ticks. So U is in the middle of the 3rd tick, and V is in the middle of the 3rd last tick. If you count the number of ticks, you will find there are 10 ticks between U and V. So the time taken is 10 times 0.02, which is 0.2 seconds. And therefore acceleration is equal to 100 minus 50 over 0.2 seconds. That gives us 250 centimeters per second squared. Lastly, we'll look at finding velocity and acceleration using a ticker tape chart. Now the ticker tape is cut into strips, each with 10 ticks. And remember, ticks are the spaces between the dots. They are then arranged this way to form a chart. The frequency is set at 50 Hz, meaning 50 ticks per second. So each tick is 1 over 50, which is equal to 0.02 seconds. It means 10 ticks will be equal to 0.02 times 10, which is 0.2 seconds. So we label the time on the axis as 0.2 seconds, 0.4 seconds, 0.6, 0.8, and 1.0 seconds. First, we need to calculate the total displacement. As you can see, for the first strip, the displacement is 20 centimeters. Second strip is 18 centimeters. Third strip is 16 centimeters. Fourth strip is 14 centimeters. And the fifth strip is 12 centimeters. So it's pretty easy. Total displacement is the sum of all these individual displacements. So we add 20 plus 18 plus 16 plus 14 plus 12, giving us 80 centimeters. This means the whole strip was 80 centimeters long, but was cut into 5 strips, each with 10 ticks. Next, what is the average velocity? We already know that the total displacement is 80 centimeters. Now all we need to know is the total time taken. As you can see, we have 5 strips and each has 10 ticks. So we have 5 times 10 ticks, giving us 50 ticks. Each tick is 0.02 seconds, so 50 times 0.02 gives us 1.0 seconds. Average velocity is given by total displacement over total time taken. That is 80 centimeters over 1.0 seconds, and that gives us 80 centimeters per second. Next, we move on to find the acceleration of the motion. To calculate the acceleration, we need the initial velocity, final velocity, and the time interval between the two velocities. The first strip represents the initial velocity u, and the last strip represents the final velocity v. To calculate the initial velocity, we calculate the average velocity for the first strip. Average velocity is given as displacement over time. The displacement here will be the length of the strip, which is 20 centimeters. Time taken is 10 ticks times 0.02 seconds, giving us 0.2 seconds. So the average velocity will be 20 centimeters over 0.2 seconds, giving us 100 centimeters per second. To find the final velocity v, we do the same thing with the last strip. Its length is 12 centimeters and the total time is 10 ticks times 0.02 seconds, giving us 0.2 seconds. So the average velocity will be equal to 12 centimeters over 0.2 seconds. That becomes 60 centimeters per second. Now the time taken. And this is where it gets tricky once again. You cannot just take the total time, which is 1 second. Remember that we want the time taken for velocity to change from u to v. We used the average initial velocity and the average final velocity. So the starting point should be the midpoint of the first strip, and the end point should be the midpoint of the last strip. So from the midpoint of the first strip to the midpoint of the second strip, that is 1. And the second to the third strip, that is 2. Third to the fourth, that is 3. And from the fourth to the fifth midpoint, that is 4. So the time taken between the midpoint of the first strip and the midpoint of the last strip is 4 times 10 ticks. And every 10 ticks is equal to 0.2 seconds. So we have 4 times 0.2, giving us 0.8 seconds. And now acceleration is equal to v minus u over t. 60 minus 100 over 0.8 gives us negative 50 centimeters per second squared. So the motion was a deceleration. And that is true because, as you can see, the dots get closer and closer as you move from the first strip going to the last.